regression and how it works. Today, we want to look at just three different types of regression. So, what is regression? Regression is actually a model that predicts an outcome using some input values. For instance, if I have, let's say, if I have a value here, x, and over here, let's say y. So if I have this place, let's say 6, I have over here 8, and I have here, let's say 10. And then if I have also on this side, let's say I have 3, and I have here, let's say 4, and I have here, let's say 5. So I'm simply just trying to know or to see what is the contribution of x here to the output that we're seeing here. I have 2 here, and then this place is 6. So it means x may be 3. Then if we come to this point, this is 8. So x may be 2 here. And then this is 10. X may also be 2 here. So here, x is actually predicting y. And because of that, x become our predictor, y become our response, which means each time x changes, y will have to change. But when y does not depend on x, y depend on x doesn't depend on y. So because of that, x is called independent variable, y is called dependent variable. In other cases, x is also called a predictor and y is called a respondent. Any of them is fine. So that is regression, and then just pay attention to those terminologies. Whether you hear independent or you hear predictor, it's the same thing. Whether predictor. So here you can, if you hear independent, the other side will be dependent. And then if you hear something like a predictor, the other side will be called response. Response. And then in that order. So we can have one predictor. So when I'm using one, I will just be using that one. We can have one predictor and then one response. For instance, I have only x here as my variable, and then I have y here as my other variable. So once I have only one predictor and one respondent, it is called simple linear regression. There are instances you can have the predictors to be many. For instance, I can have x here, the next column is also x, the next column is also x, and then the last one is y. This becomes multiple linear regression because you are looking at different predictors and then one respondent. And that's how it works. There are also instances you can have x here, and then the next x here, it will be x squared, and then you have your respondent, which is y. This one is called polynomial regression. That is when you are measuring growth curve and then other things. Then that becomes our kind of regression we're going to look at. So simple linear regression, just two variables, dependent, independent. Multiple linear regression, one dependent, different independent variables. Polynomial regression, you have two predictors, but one is a square of the other, and then only one response variable, and that's how it works. So now let's quickly look at one of them. Let's quickly look at simple linear regression. And like I explained, the simple linear regression is that let's look at pesticides in lettuce and the number of crates of tomatoes that somebody harvested. In this case, tomatoes, the number of crates of tomatoes that we have harvested, it depends on the pesticide that was sprayed. You see, so you spray it. So the pesticide is measured in liters. Tomato crate is measured. It's measured in crate. So when we're having 5, we have 24 crates. 10, we have 40, and then in that order. So we want to know what is the exact contribution of pesticides, what is it to the yield of the tomato yield measured in crate, as we see here. So once we have just two variables, so obviously on top here that will be x, and then this will be y. And so because we have just only x and then y, then we are looking at simple linear regression. And to be able to do simple linear regression is simple. Go to your data tab, you come to data analysis, come and click on regression, and then click OK. So it's going to, you are going to have input y range. So we've seen y here, then input x range. Then we see x over there. That's for simple linear regression. So I'm going to cancel whatever that is there. And then we start at fresh. So I'll come and click inside the input y range. You see? So I'm looking for the y. That's for the y. And like I said, this is where the y is. So I'm going to start from here, then highlight it all the way to the last point, and then we leave it. We come and say input x range. So I'm picking my x range from here all the way. But you realize that I'm highlighting all of them with their headers. The headers are the pesticides and then number of crates. So because of that, this place will have to be checked. Labels have to be checked. And then confidence interval also checked. Output range. If you want, you can get the output in the new worksheet. If you want it in output range within the worksheet where you're working, you just click inside here where the cursor, the output range text box, the text box next to it. And now select the place where you want the output to appear. I want the output to appear from here. And then that's it. I'll just click on that empty cell. So I'm done. I'll click OK. And that is it. My output is now ready. Once it is still highlighted, I'll press my alternate key down and press HOI just to make sure that it fits. And then that is it. So now, what are the most important values to look for? The adjusted R is and adjusted R squared here. Those are the most important values we need to look for. So I'm going to highlight that. Then this is R squared, which is the same as the adjusted R squared. And so what do? The adjusted R, let me give it a little bit of a different color, is the model, is it tells us the contribution of the predictors, which is x in y. So whatever variation that we are seeing in y can be explained by x, by this particular value we see here. It means 91% of the variation we are seeing in y can be attributed to x, which means the contribution or the yield that we are seeing, that's the tomato yield that we are seeing, I mean, 91% of it can be accounted by the number of liters of pesticide that were sprayed. So we can simply say it is the strength of the model, but this is the ordinary explanation. Maybe somebody will ask, what is the rationale for this particular multiple? It's actually the correlation between the predicted and the observed. Now, over here, the standard error, that is the actual prediction error. So that which is 2.35. That's the predicting error, and the observation, that's the total number of values that have been involved. That's 20. Now, when we come to ANOVA here, the ANOVA here, we have the regression, we have the residual. That's the unexplained variation. The regression is the explained variation, and we have the unexplained variation, and then the total variation that we have. So now, the most important value there is the significant F. That's the p-value. Looking at the overall model, whether the model prediction is significant or not. And you can see 3.5 to the power minus 11 means 0.00000000, 11 zeros before 3, way lesser than 0.05. So which means the entire model is very significant at this particular strength, 91.2. So that's the values that you need to pay attention to interpret. And then the other values to interpret is the intercept. The intercept value, which is here. What does that mean? The intercept value means that, oh, sorry, just to, the intercept value means that without spraying without spraying a liter of pesticide to your tomato farm, you could harvested 7.72 or 715 of tomatoes. So that is when the predictor is 0. When you are contributing nothing, then when the predictor or the input, it was 0. Now, what is the meaning of this value? That's the coefficient here. the coefficient as you can see on top here. And this is the coefficient of the pesticide. It's 3.348. Let's say 3. Coefficient here means that once it is positive, it means for every single liter of pesticide that is sprayed, it will result into 3.35 crates of tomatoes that will be harvested. And that's what this coefficient is all about. And then the other. So we come to look at the other important variables we need to look at is the p-value. The intercept here, we can see the p-value is 0.00, which is very significant. And as well, the p-value too for the predictor is also very significant, as just the same as this. Because it is only one variable, it will definitely be the same. And so that is how we are able to interpret or make sense from whatever we are dealing with, simple linear regression. This is just the simplest. And then please keep this explanation up. And then if you want us to do it again, I can come to another section here. I've already done it, but let me delete the whole of this. And then I'm going to come to my home tab, come to this point and say no border. And so here we are looking at, I think, let me remove this out. It wasn't there, I said. And then I'm just going to shift this backward like this. So that's also another simple linear regression. You can see these are the total number of customers somebody is getting at his workplace. And then the person just want to know the contribution of social media to the total number of customers you are getting in a center. So let me widen it a little bit. And so when you advertise it 3 times on social media, you are getting 21, 3 times 22, and the other. But you want to have a model that you can predict if I happen to have to let's say advertise like 11 times, what is going to be the total number of customers I'm likely to get. That's a regression. You want to just produce that kind of model. But once we are having only one response variable and one predictor, it's going to be what? Simple linear regression, like I mentioned. So you go to your data tab, come to data analysis. Oh, why? I think, okay. You go to your data analysis, come to regression, and click OK. As usual, I'm deleting whatever that is here, deleting whatever that is there, and then in that order. Then let's move to that side. And my input was input Y, that's the response, which are the number of customers. So we highlight from here all the way to the last one. I have a so we highlight all the way from here up to later. And then we can now see again, come and look at your R squared, 95%, and then adjusted R is also 95%. So these two values, especially this particular one, the adjusted R, which is the model, that's the strength of the model, explaining whatever that has happened to all the total number of customers that you are seeing here is as a result of the social media advertisement that you are making. And what is the strength, or how, of what proportion can you say that social media actually can explain whatever that you are seeing in the total number of customers? Is by 90.6%. As you can see the value here. And then that's how we look at it. Again, we come to look at the overall model strength is 7 raised to the power minus 14, which is 0.0014 before. Very, very significant, which means the social media is actually contributing a lot to the output or to the total number of customers you are getting. Now, let's come and look at the intercept. The intercept here tells us that without advertising on social media, how many customers you are likely to get? About 3 customers, as you can see the value around here. Now, look at the coefficient. It's telling you that for every time you advertise once on social media, this is the resultant number of customers you are likely to get. 6.67. That's a 7 customers you are likely to get. So each time you advertise on social media, that's the coefficient of the social media, as you can see here. And you come and look at the p-value, but the p-value is not significant, even though the the predictor p-value is significant at 0.00 in that order. Now let's look at the the let's look at the equation here, the model that we're looking at. So the equation, you can now write it this way. You can say y is equal to, remember it's always a plus bx. The x is the predictor, and then the y, sorry, I'm saying the y, the b is the coefficient, a is the constant. Now in this case, y, let's put it in proper context. Now we have our y equal to, the a is the constant, which is the same as the, what is it, the intercept. So our intercept is 2 point, let's just put it 2.9. So it's going to be 2.9, and then plus the coefficient is b here. B is the coefficient. And what is the coefficient? It is 6.67. So that's 6.67. 6.67 of what? X. But X is the predictor. What is the predictor here? Is social media, SM. So social media, SM over there. And so that's the model. That's what we see it here. Now let me increase it a little bit, and then you can see the model. Increase this a little bit, and then that's the model we are seeing around here. Now, to now put it in real sense, for instance, we were saying that if we advertise 11 times on social media, what is the total number of customers we are going to get? So social media becomes 11. So we can come here and now put it inside there. That is why we produce models, to be able to have a prediction. So I'll say equal to 2.9, you see, plus 6.67 multiplied by what? The social media, number of times you are doing. And in this case, we are talking of 11. Tap enter. So it means when we advertise 11 times on social media, we are likely to have 76.27 of our customers. Let's say 76 customers that we are likely to get. So that is why we produce model, to let us be able to predict ahead of time what we are likely to get if we are able to do this. So we do that by generating the data, then do our regression in the case of simple linear. And so that is for simple linear. Let's look at quickly multiple linear regression. And so I'm going to take out the whole of this as usual. Then remove all the highlights, and then remove all the borders. Now, in terms of multiple linear regression, you see that I was hiding some data where I kept the borders. Okay. And so now, let's hide the whole of this data and then unhide it. And then, okay. Now let's leave it that way. So in this case, we are now having how many predictors? And I think the borders are just, it's looking, it appears as though it is standing aside. So now let's look at, in the case of multiple linear regression, we have one response, like I explained, and then many predictors. The predictors are fertilizer, labor, and pesticide. These are all input that resulted to data analysis. Pick our regression. We are just going to the number of creators, our single response variable, and pick the whole of fertilizer all the way to pesticides as our what should I say, our predictors. But then there are some few things that I will need to explain. Before you can do a multiple linear regression, know this. There are certain conditions that must be met. The first condition is that the predictors must be in sequential order. You cannot have fertilizer in column G, labor is in column K, and then your response variable, which is number of crates, in column E. No, it is not permitted. Make sure that all the predictors are in order. For the one, the next, and the next, and the response variable, all of them put together in a sequential order. So they are not separate. There's no empty column separating them. And there must not be another variable that is found between them. No. The variables that are going to be involved in your regression must follow. The predictors on one side, the response on the other side. And that is okay. The second condition is that do a multi-collinearity to ensure that none of the predictors have direct correlation to each other. So what I mean is that the predictors here are fertilizer, labor, and pesticides. When you do a correlation analysis, none of them should be directly correlated to the other. If one of them is directly correlated to the other, whether negative or positive, drop that particular, drop one of them, because there will be no need to have values or variables that are directly correlated, because they will perform the same way. They will all have the same prediction. So what is the value of putting? Just use only one. This is what I mean. For instance, I could come here, come to data analysis. Now come and look for correlation. Correlation is here. And then I'm just going to cancel all of that. And then, first of all, you need to come and then we are checking all the predictors to see whether is there any correlation between them, or I highlight at a different place. So all the predictors, and then any other thing here is okay. You make sure that by columns, then you have labels headed. Then I want my output to appear here, and then I'll simply just click OK. Now come to look at it. These are the correlation, but the one they are not necessary. We are looking at this, and so you can see, okay, let me. So if you check, you can see that none of them is directly correlated. But if you cannot see it this way, let me come to my home tab and convert it to percentages. This way it's easy to see. Now the 100%, forget it, because that's fertilizer will definitely be 100%, and that's not the point. We are talking of fertilizer to labor is minus 17. Fertilizer to pesticide is minus 7. Labor to pesticide is, I think, 83%. It's not up to 100%, so we can use the two of them, and then in that order. But if we had 100% here, 100% there, 100% there, or one of them being 100%, let's say labor and pesticide being 100% here, we would have dropped one of them, either labor or pesticide, and we will not use the two. And that's what I mean by, so you need to check multicollinearity to see that they are not, so before you be able to go ahead with your multiple linear regression. Another condition is that the total number of rows and columns must not be the same. For instance, if you are going to do multiple linear regression, we are talking about 3 predictors, 1 response variable, put together 4 columns. So the number of rows that contain the data you are going to run must not also be 4. For instance, where I have highlighted red, if I pick like this, where I've highlighted red, it means that we are having how many rows? 1, 2, 3, 4. How many columns? 1, 2, 3, 4. So in that case, well, you can't conduct multiple linear regression with that kind of data, because the total number of rows are equal to total number of columns. So you cannot do that. If you do, you're going to get errors throughout, and then in that order. So that's the other condition. Now let's go ahead. Having known the 3 conditions under which you can conduct multiple linear regression, Now let's do 1. And all our conditions here are met. So we can go ahead and then do it. So I'll go and come and click on my data tab, come here, come to and look for regression. And then regression is here. I'll click on that. And then my Y input range is the number of crates. So I'm going to click on the up arrow. So it's always good to delete everything that is inside it. And then I'm coming back to that place. So my response is the number of crates. And then the predictors are fertilizer, labor, and then pesticides. All of them, we have to highlight all of them at once. You get it? Like this. And that's my input X range. So you highlight all the predictors at once. We highlighted with the labels, as you can see. So you have to check labels, check confidence interval, then output range. Where do you want the output to appear? I'll click inside that particular box. While the cursor is blinking, I'm going to select this. I want the output to start appearing from there. Any other thing, fine. If you want to see residual plots and everything, you can click on them and then you are good to go. Other than that, just click here. And then this is our multiple linear regression. So we come to look at it. Like I said, the adjusted arrow, but let's start with the multiple arrow here. Like I said, it actually tells us the correlation between the predicted and then the observed. The R squared and then the R adjusted. The R adjusted is what is always often used. Very important. It means 90% of whatever variation that we are seeing in the response variable, which is the number of crates of tomatoes harvested, can be explained by the predictors. And so that's the strength of the model. Also telling us the variation that we are seeing in the response variable being explained by the predictors. Now, what is the standard error? That is the prediction error. And then in that order, observation plus total number of samples included. Now, and over here is the overall significance. So we come and look at the overall significance, which is significant F here. And minus, raised to the power minus 0.9 means that the overall model is significant. The regression actually explained that the explain variation, telling us that all that we are seeing in the response variable can be explained by the predictors, and that particular explanation is significant. Now, residual is unexplained variations that we are seeing in the response variable, and then this is the total variation. Now, these are the most important areas. The coefficient. The coefficient is telling us that without fertilizer, labor, and pesticide, the person could have still harvested 8.199 of the tomatoes that the crate of tomatoes that we are talking about. Then fertilizer would have, for every kilogram of fertilizer that we have, it will result into 0.0. It will result into this particular what is it, amount of total number of crates that we are likely to get. So that will be 0.003. I'm always disrupted by this ship. I don't know. Each time I want to record a video, that's the time the ship will just come and I don't know. I'm sorry about that. Labor hours, you can see that it is minus, telling us that the contribution of labor is actually resulting into a reduction in the total number of crates. That's why it is minus here. Pesticides will contribute a lot. Now let's come and look at, if you are actually going to produce a model, what of these input variable will you include in the model? When we come, p-value here is not significant. The here is not significant. Here is not significant. We come and look at pesticide, and the p-value is significant. Raised to the power minus 6 is significant. So in that, for that matter, if I were going to produce a model, I would say fertilizer has no effect, labor has no effect on the model, only pesticide has an effect. And then I'll simply just put what they do that, include it in my model. And that's how we do multiple linear regression, and that's how we interpret it. And then sometimes we do it to either include or exclude some input variables and say that, okay, this one doesn't have any effect on my output. This one contributes nothing, and then in that order. So that's how it works. I don't know if I have time. Let me still do the other ones. So let me see if I can delete the whole of this and then come to this point. and then also remove the highlights, no fill anywhere. So now let's see if we can also do the polynomial regression. Polynomial regression is done when you are working on growth, like growth curve. But how is it done? It's like multiple linear regression, but you are using the same variable, the variable and the square of that variable to look at the impact on the response variable. So you have a predictor, then you square the predictor. Now use both the predictor and then the square of the predictor to be able to their contribution into the output. Now, this is what I mean. I'm going to highlight this, shift it to this point, and you see that my predictor is social media. The response is the number of customers coming. And square. So I'm going to, all right. So now when I come here, I'm simply going to say, I'm going to square all of the SMS values. So press your shift key down 6, then put 2 there, tap enter. Then come to this point, double click, and then that is it. So now we are now going to look at the our customers as our response, and then the social media as a variable and social media square as a variable. So we've squared the predictor, and then so anytime we are using a variable and the square of that variable to predict the response variable, then we are doing polynomial. And this kind of regression is done when you are looking at growth rate. For instance, the changes that occur when you are giving feed to an animal and you are checking their growth rate. Like if you have applied a particular pesticide, then you are checking the number of pests that are found on the leaf. Those of us who do what is the microbiome analysis. Then maybe you apply some kind of a hand sanitizer, and you want to know the total number of bacteria that will likely grow or will die, and then in that order. That's growth. And then we use polynomial. But here I'm just using an example for you to see. So this is how we do it. It's practically the same as multiple linear, but it's the same predictor, and the same predictor has been squared. Now let's come and then do that part. And then so we click on our regression, and then let's come to that point. So in that case, we come and click inside our input Y range, which will be our customers here. And then our input X range will now be the social media and then social media squared. And then in that order, our output range, let it just be here. And then everything in order, then we click OK. And then we can now have we can see that the predictor squared is actually not contributing anything. It's actually reducing the number of what is it? The number of customers that a person is likely to get. But it's the same explanation as I just wanted you to see how polynomial regression is being done. But this is not the best data. I should have looked for a data that has to do with growth rate, like the number of what is it? Like I've already explained how we could measure it. But that is the same explanation as you can see, even though the model is a little bit strong. And then the overall model strength is also strong, as we can, it's also significant. But if you look at individual, we can see social media is still, significant, but the social media square value is not actually significant. And the intercept too is not also significant. Yeah, but that's it. That's how we conduct regression, simple linear, multiple linear, remember the conditions, and then polynomial. The other regressions like logistics, regression, which we actually have a binary outcome, like present, absent, male, female, survive, dead, or all of those things. We can't do that one in X, but you can do that in R. So that's it. And then thank you for sticking around. I'll see you.